Okay, we're starting. I have your test. I'll give you at the end of class though, because I don't want you to be distracted reading through while we're going through stuff. So we are going to move on to 13.6, parametric surfaces and their areas. First we're going to learn how to parametrize surfaces. By surfaces here, you of course remember, what is a surface? What kind of object are we talking about if I say a surface? How do you describe a surface? A sheet. How many dimensions would it have?
Are you on the surface or off the surface?
Surfaces have 2 dimensions, okay? So it's like a plane is a surface, something that has 2 dimensions, okay? So if I'm talking about a parametric version of something that has 2 dimensions, how many parameters do you expect there to be? 2 parameters, right. The number of parameters in general will be the dimension of the object that you're talking about, which reminds me of something that I saw on the test a lot, where I asked, there were times when I asked about a plane and people gave me the equation of something with 1 parameter, which kind of tells me that there's a lot of misunderstanding there. Okay, so if something has 1 parameter, it's not a surface. Something with 1 parameter is a curve, that's 1-dimensional. Something that's a surface has 2 dimensions, so you'll have 2 parameters. Something that is a solid will have 3 dimensions. Okay, and we'll get to that. We'll get to talking about solids pretty soon. But today we're going to talk about parametric surfaces. Ultimately, we're going to want to talk about something called a surface integral, which is kind of a higher dimensional line integral, and we'll get to that. But for now, let's just go through some definitions, make sure we're all on the same page, we all know what this guy is. And so surfaces are 2D mathematical objects, which kind of means you need 2 parameters instead of 1, so that's one thing you need to mention. Originally I wrote down like 2 paragraphs in my notes about that, but let's just skip that part. And I will define essentially what a surface is. So we like to start with the mathematical definitions here. So let x, y, z be continuous functions of, I'm going to call my 2 parameters the names u and v. Right? You can call them by almost anything. Which have domain D in the UV plane. Okay. Then the set of points that have this form R of UV is equal to your x variable will be thought of as a function of 2 variables, your y variable will be thought of as a function of 2 variables, your z variable, your z coordinate will be thought of as a function of 2 variables. So that's the set of points. Is called a parametric surface. So intuitively, a surface is just a 2-dimensional object. Mathematically, it is a vector function that has 2 variables in it. The equations x equals, mention the function of uv, y equals, mention the function of uv, z equals, again, similar language, these are called the parametric equations. So you can express a surface as a vector function. You can also express it as a set of parametric equations. The difference is how you know something is a function. There has to be two variables present, right? At least one of your variables need to have like two variables present. Okay. If you don't have two variables present in any of them, it's not a surface. If you have more than two variables, it's also not a surface. Okay. The idea is the same also as a vector curve, but this time it's some sort of sheet hovering in space where the vector r of uv for a certain point give you a point on that surface. So this would be a vector of r of some point u naught v naught. Okay. And when you take all these points together, they form a two-dimensional surface. Did any of you guys do parametric surfaces in Calc 3?
No.
No? Sometimes it's a topic that you skip, sometimes your professor might cover it. But one thing they just take from this chapter is the formula for the surface area. Right? So this is the chapter where you get that formula for the surface area. Where you get that guy that was a equals the square root of 1 plus the partial of x squared plus the partial of y squared. That formula, when you take the double integral of that, it comes from this chapter, but we'll derive that later, right? But usually in Calc 3, they just literally take this one formula, like, okay, we did 13.6. Yeah. Okay, so I just want to know whether anyone has seen any of this before. So that's basically a parametric surface. Let's do some examples. So the basic examples exist here. So you know that if something has some sort of circular cross-section, again, you're going to use sines and cosines. If something is a plane, it would look like the equation of a plane, etc. So I just want you to remember some general forms. So let's talk about one of these. It's nice to learn by just doing here. So here you're given a parametric surface. I'd like you to figure out what it is, and we'll sketch it. Let's just do that.
Professor?
Yes.
One that's a cylinder, no? It's like one of those stretched out cylinders.
It is a cylinder.
Okay,
Yes.
but I do have a question aside from that. On the very beginning of the class, you told us to print out this one sheet with all of those surfaces to identify. It was 10.6, I believe.
Yeah.
And it had the, like, when you're gonna parametrize, and it had like a list of stuff. So
Yeah.
we've been discussing lines, circles, what about ellipse? Because I know parametrizing, different shapes are different, and over the homework there were ellipses, and we never touched on it, but it makes the parametrization just a little bit different. And I forgot how to complete the square.
Okay, so that's another thing. Whenever you have an ellipse, what's going to happen is your r would be different. So you're
So
going to
how,
stretch
like-
along another axis.
So, well, because it comes up in the homework and in some of the problems, and I don't remember it. So
Yeah.
could you
So
tell
it-
us that? Give
Well,
us the answer?
Not really, but
Well, I mean-
10.6. If you have a question about a specific problem, just see me in private. But in 10.6, yes, you need to go over that. That was in the syllabus. We're not going to really be touching on every single surface in there. So I can tell you that you need to know about planes. You need to know about cylinders. You need to know about paraboloids. You need to know about ellipsoids. You need to know about spheres. Pretty much things that you don't need to know is like hyperboloids or hyperboloids of two
Cones
sheets or
still?
cones. You need to know about cones.
How to parameter them by ourselves without your help, basically.
Yes, and how to sketch them and figure stuff like that.
Okay. That was the end of my question. And it's a cylinder.
Yeah, so things like hyperboloids we won't really look at too much. And hyperboloids of two sheets we won't really look at too much. But yeah, the things that are the nice, like platonic solids. Alright, so you should know about cubes, spheres, cones.
Platonic isn't nice. Nothing.
Platonic is nice. That's like the definition of the word. The really nice solids.
Oh.
We call them platonic solids. Anyway, so this is a cylinder. Can you kind of explain how you figured that out?
Because R is 3 and V is Z. It's gonna be like so it's gonna be a circle. It's a circle. Okay.
Okay, so you said that V is Z.
And the height is
that's
5
kind of,
on Z. The height is 5. We go from 0 to 5 with a
Okay.
radius of 3.
yeah, so that's what we're going to do. If you look at this as a parametric equations, for example. Basically what this is telling you is that your x value is giving you 3 cosine u, your y value is giving you 3 sine u, and that should remind you of a circle. Right? Now it tells you your z is just this value v. And so what you can see is here, because this variable has nothing to do with that variable, this is telling you you're seeing a circle for all z values. So the idea is you have a circle of radius 3 when your z is 0, you have a circle of radius 3 when your z is 1, when it's 17, when all the time. For any z value, you have a circle of radius 3. However, we've restricted the z value to be from 0, so that's in the xy plane, up to 5. So let's just call this 5. So that's where z equals 5. So the idea is if you're looking in the xy plane, so if you're looking down, right, in the xy plane, you'll just see a circle of radius 3. And this shape is being propagating along the z-axis. And then I restrict how far we can move along the z-axis with the v. Okay? You also know that this has to be a surface because there are 2 variables, that's a u and a v. If this was something else, like a 1, it's no longer a surface, it's now a curve. Right? That would just be the circle of radius 3 that's hovering in the plane z equals 1. Right? But with 2 variables, it's now a surface. Okay? So that was the first example. And again, this idea will kind of be constant. All the patterns that we learned from curves, we're applying them here. It's just that we're propagating that drawing along some sort of axis, usually. So all the tricks we learned from the single variable things, from the single variable curves, we will apply here. You should just, so this means, of course, you'll have to remember what the equation of certain things look like. What does a circle look like? What does an ellipse look like? What does blah, blah, blah look like? Once you can know it in 1 dimension, or in 2D, you can kind of extrapolate the 3D shape. Okay, so that was good. So this is called a right cylinder. You can think of this as a general form, for example. So if you see something like r uv is equal to r cosine u, r sine u, and some v. So this is just a guy that, it's a cylinder that's running along the z-axis. R here is a constant. But of course notice that in 3D things can permeate. So for example, you could have the cosine here, the v in the middle, and then the r sine down here. And what would that mean?
V on his stomach.
It's running along the y-axis. So that would mean the cylinder is going this way. And again, I can talk about another formulation. The v can be here, r cosine, r sine, and this just means you're running along the x-axis. Right? So you have a lot more angles to worry about in here when you're in 3 dimensions, but that's kind of how it goes, right? So you're just noticing certain patterns. You notice that sine and cosines kind of create circles, and then you kind of figure out from there what's going on. Here's another one. So it's you taking advantage of knowing about a certain pattern, and you're going to apply it in 3 dimensions to create a 2-dimensional surface. Identify and sketch. I'm going to be very suggestive with the notation here. So R I'm going to let be a function of phi and theta, and we have sine phi, cosine theta. Sine phi, cosine theta, sine phi, sine theta, and cosine of phi. And what's that?
Sphere.
Sphere? How do you know sphere? What reminds you of sphere? Right, kind of reminds you of spherical coordinates. You would notice here, if you take x squared plus y squared plus z squared, you get 1, and so you notice that's a sphere. So this is a generic way to do a sphere. You can just use spherical coordinates. So that's just a sphere of radius 1. So in general, you could call a sphere of radius r by sort of abuse of notation here, but this r is a vector. So it's r sine phi cosine theta, r sine phi sine theta, r cosine phi. And this just basically is inspired by spherical coordinates. What else do we want to do? Here's another one. And so, yeah, we can sketch that. So spheres will be very common, cylinders will be very common, so this is just sphere, radius 1. Especially if I give you the limits. Here are your phi. Okay, let's remember a little bit from spherical coordinates. What is the range of your phi here if I want the full sphere?
0 to pi.
0 to pi. And this guy is just like before 0 to pi. So this is at 1, that is at 1.
Professor, why phi is 0 to pi?
Spherical coordinates. Phi is measured from the positive z-axis down to the negative z-axis. That's the maximum range.
Wow.
Theta is the same guy in the xy plane that you know about the angle in the xy plane. And then your r here, or usually rho is what we call spherical, is just the distance from the origin to the outer surface.
Positive x-axis to the negative z-axis.
What about this one? R of u v.
Is that a cone?
It's a cone. Here you just have your x equals u, your y equals v, and so your z would be the square root of x squared plus y squared. This is a cone. Right? By the way, this is taking advantage of, and it's only the top part of a cone, so this just goes up that way.
Wait. Don't erase it. Radius r. What is that? R theta?
Here?
No.
Where?
After the general in sphere
So
of
this
the
is general.
Okay.
This is R of phi theta,
R,
and this is inspired.
R,
In other words, you need to remember all your coordinate systems from calc. It'll make
Okay.
things a lot easier to identify.
But Professor, what specifically do you want us to know from the past? Because, you know, it's like,
Too much.
I just told you.
no, you're saying, but I mean, to you mean all of that's like all of calculus 3.
I never said all of calc 3. At no point did I say all of calc 3.
No, but like from what you're saying is like, you know, with these coordinates and stuff like that and these shapes, like in the homework, a lot of it comes back up. With area and velocity, like it's a lot of calculus 2 and 3 in there. So it's hard to remember all of that and then this. It's like if you don't remember that, you can't do this.
Exactly. That's literally what I said the first day. Exactly. Exactly. You're not going to do well in this class if you don't remember your calc 3. There's no ways about it, and I can't teach you calc 3 before teaching you this. You just have to figure out how to remember. You need to know everything about surface, about multiple integrals, and of course partial derivatives, and the kind of things that you would see on the reviews, basically. So series you won't really need to remember for this class, as well as nothing that's really a super specific application. Like you're not going to need to remember how to find maximums and minimums of multivariable functions, really. So just you need to know how to differentiate, find partial derivatives, know how to do integrals set up in multiple coordinate systems. You need to know about the surfaces, how to find volumes and areas. Okay, so the one I started here, let's just say this one. Anyway, at the end of the day, you will know if you kind of just follow my syllabus and follow the materials that I give you. You'll know what you need to know. Like nothing's going to be a surprise. So if you look through all my review problems, all the final exams that I told you, all of the materials that I put on my website, you're like, oh, I don't notice this topic is there. It means you don't need to know that topic. You'll notice, for example, there is nothing in all of the materials that I post that requires you to know how to find the maximum and minimum of a multivariable function. So you know, oh, I don't have to remember that.
The homework did ask for a max, actually, just to put that out there. The homework asked for a maximum value from the
Of
ellipse
what?
question that I'm talking about. They did ask for a max value at A equals, and I didn't know how to find it. I used Slater, but we do, well,
What's Slater?
it's, you know.
Is that like another website?
No,
Is it like Chegg?
nothing for specifically, but I needed extra help. It's online tutoring. You know, you can ask, you know, some questions for help, for if you need assistance.
So it's kind of like Chegg, but
Okay. But it did ask for a maximum value of an ellipse, which you didn't teach.
okay. So yeah, if you guys know websites like that, you should tell me. I want to like put them in my syllabus and stuff. Okay, you can check Slater. You know, as much as I can direct students to other resources other than me, these things you need to tell me. Oh yeah, there's a website called Slater. Okay, that's nice now. This showcases a general principle. Again, this is kind of like, remember back in single variable function, when we were doing curves, I told you one way you can parametrize a curve is to just let one of the variables themselves be a parameter, and then you can just write the other variable in terms of that parameter. The same thing can apply here. So the idea is, if given some sort of function like z is equal to f of x, y, and this is a surface, of course, because it has two variables, then we can parametrize by just saying x equals u, y equals v, and z is equal to the function of unity. You have that option all the time. And of course, you can swap variables and the same thing will work. So if you have something like, if you can solve for y, and I'm kind of glossing over this, but this is actually a super important idea. We'll return to this idea when I talk about normal vectors. So if you have y is equal to some function of x and z, you could also do something like x is equal to u, z is equal to v, and then set y is equal to the function of u and v. Right? You always have that kind of option. Just let the variables themselves be parameters, and then plug it into some function that you know of before. Knowing that idea will help you with normal vectors. Let me just give you the last one. So if your x is a function of y and z, then you can set y equals u, z equals v, and x equals the function of u and v. So if it's some sort of pattern that you don't recognize, like it's not sines and cosines, you can't really see it as a circle. Or you notice it's not spherical, so you can't really look at it as a sphere, or something like that. Try to think of it in terms of this principle. Right? What if I just take the x and the y and I plug into the other nasty function? Can I simplify that to a curve or a surface that I know? Right? So that still applies here. So takeaway here. Let me sort of just summarize what we want to talk about. So the idea is, again, you want to find patterns, right? So one, if you see sine and cosines, try to get a circle out of it. Right, and then you can use the third variable. Also, get inspiration from coordinate systems. So if something reminds you of cylindrical coordinates, odds are the surface is a cylinder. If something reminds you of spherical coordinates, odds are the surface is a part of a sphere, etc. 3, you can set 2 variables, right, as opposed to 1, equal 2 parameters, and solve for the third variable. Right, so patterns like that. So it's kind of the same principle that we did with single variable vector curves, but now you're just applying it to 2 variables at a time.
Is that what you did with z in the cone?
That's part 3 is what I did with z in the cone. This guy is what I did with the sphere, and this guy is what Benita figured out for the first attempt. Right, but these are the general patterns of the ideas that you want to use. And usually it's not going to be something too crazy. It'll be some sort of nice surface, but you need to know the basics. You need to recognize spheres, cones, planes, things of that sort. Planes, by the way, is something that also might come up. Right, so you can be given a point in the plane. Something like x naught, y naught, z naught. And 2 vectors that are not parallel in the plane. You can call these vector u and v. So if you have a plane, there's a point right here, x naught, y naught, z naught. You know two vectors in the plane, like one you can call u, the other one you can call v. Then it turns out you can find a parametric equation for that plane by you put the point x naught, y naught, z naught, plus something like t times u plus r times v, or s times v. So you multiply each of these vectors by a scalar and add it to the point, leave this as a vectorized function, and that can parametrize a plane. That's given the case that you know about two vectors in it. If you don't know two vectors in it and you just know the equation of a plane, you can always use part 3. So if you have something like so let's say you know, 2x plus 3y minus 4z equals 5. You know that's a plane. Hopefully you know that's a plane, because on the test I asked you to find the equation of a plane and people didn't give me anything that looks like that. So you know this is a plane. You could always, technically from this you don't know two vectors in it, but you can always do this kind of trick. And so you just say, set x equals u, y equals v, which would mean that if you solve for z, you get your z to be 5 minus 2x minus 3y all over minus 4. And so you could parametrize this plane by u comma v comma 5 minus 2u minus 3v all over minus 4. Right? Still an option. And by the way, once you actually jump to that, you can realize a lot of nice things can fall out of that equation. Notice that you can write this as something like 0, comma 0, comma minus 5 over 4, plus you can take u times 1, comma 0, comma a half, and you can take v times 0, comma 1, comma 3/4, for example. Right?
Professor,
Yes.
what is this t u vector and
T and S are just parameters.
Okay.
They're just scalars,
Okay.
right? U and V are the vectors that you know is in the plane. You can parametrize a plane this way. If you're given the plane in the scalar equation form, you can just let each variable be choose two variables to give you parameters, solve for the third variable. You can throw that huge thing in a vector. That's another way to parametrize a plane. Once you know how to parametrize a plane this way, you can actually split it up into the constants, the guys with the U's and the guys with the V's, and you automatically get this form, which you can automatically just figure out from this equation what's a point in the plane and what are two non-parallel vectors in the plane. If you ever need to know that for some reason. By the way, what's the normal vector of this plane?
Is it 2b4?
Huh?
Is it 2b4?
No?
2, 3 minus 4?
2, 3 minus 4. Okay. Things like that you need to remember.
What's a good resource for quick review of planes? Because this stuff feels so fuzzy and distant, I really don't remember much of it at all.
The textbook, pretty much. In terms of the problems, you can do the past 203 finals. They always have a problem with a plane on it, right? So there will be various kinds of problems. So they'll say, find the equation of a plane that has given 3 points, or find the equation of a plane that has a point and a line in it. Find the equation of blah, 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 blah. Right? You'll always have a problem like that on one of the 203 finals.
Do you
It's
have a
standard.
page for when you was teaching Calculus 3 up there still? That's active so we can see like some of the things you asked since you're the teacher?
There's just a surprising amount of pure Calc 3 stuff on the
I
test.
don't remember nothing.
And yeah, exactly. I don't remember anything either. It's been like 3 semesters since I've taken Calc 3.
Yeah.
Yeah, but why was it surprising? Did you guys look at the review?
I looked at the review, but it really did, I looked at it kind of before the test. And so I didn't know that I needed to reteach myself Calculus 3.
I just did web work and homework. I didn't know you had review questions online, which is my own fault. But,
I announced the first day that there's a review. There are reviews for all the tests currently up. So
No,
if
I
you want to
mean
know what's
calculus.
going on test 2, you can now look at the review for test 2.
No, not the test. I mean the calculus stuff because it keeps coming up as I'm like studying for the new stuff. Calculus stuff comes up, like stuff like ellipses, and so that's what I'm saying. If I could like maybe look back at what you taught in calculus, I would know what I don't know because I don't know until it comes up and then I don't know it.
Okay, so here's an example of how you do that, right? Let's say you're worried about, okay, I'm going into test 2 and I'm worried that there are going to be some Calc 3 stuff there that I don't know and blah, 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 right? Go to my review for test 2. You'll recognize Calc 3 stuff that I didn't teach in class there. You're like, oh, here's something that's from Calc 3 that I don't remember.
I haven't been recognizing it. I've just been looking at the review and just not knowing anything on the review. So I've been getting anxious, and I'm anxious now.
Well, if you look at it right before the test, that's exactly what's going to happen. If you looked at it a week before the test, that's a completely different scenario. Right? So on the review, there were things where I asked you to find equation of planes and find surface area. So you looked at the review, you'll know, oh, on the test, I probably need to know how to find surface area. Now you know the topic you have to look up. You can go to the past Calc 3 files, look up surface area. You can look up my math videos about where I taught surface area. You can look up Slater or Chegg or anything. You can do a Google search. You can go back to your textbook.
You
By
want us to
looking
be
at the
very
review.
self-sufficient.
Huh?
You want us to be very self-sufficient.
Yes!
Wait, Professor, instead of that, can you give us a specific topic
This is what I'm
that
saying. Yes,
What?
that's what I'm
No.
saying.
yeah, a specific topic that we need to focus on for test
Listen,
2 so that we
I
have
am not
very
doing you
limited
any favors in
space in
doing
our
that. The world gets more and more complicated the higher up you go. It is literally impossible for me to tell you literally everything you would need to know.
So how you
You
expect us to
need
remember
some
it?
sort of
Exactly,
self-sufficiency here.
we took calculus 3 like back in like 3 or 4
Years
semester ago, and
Yes, but you passed it, which means you know how to do it. Just remind yourself.
There's very limited space up here.
Anyway. Come on, you get a lot of your engineers. You think you get an engineering job, you go on the job, you're gonna be like just trailing behind someone. Oh, how do you know this? How do you know this? You wouldn't have a job for long. They're going to expect you to know. You got an engineering degree. Figure it out. This is the problem. Figure it out.
well,
Right? If you always just rely on me to literally tell you everything, what is specifically do I need to know in order to do this job?
I mean the world
It's
is open
not
book.
benefiting you.
The world is open book, open calculators, open everything, but the test is closed to everything. You need to put it in. Isn't it?
I don't have time for this discussion. That is something we can have in private. Right. So if you're an engineer and you're going to a client and you want to talk to your client, okay, let me check my engineering book. Oh yeah, so this is that. So this is that.
Those clients are going
This
to be
is that.
arts majors. I can tell them whatever I want.
And we can take some time that give us some time
So
to study.
for one, you guys need an ethics class. And for two, if you think some client is going to trust you when you can't talk with authority and confidence and know what you're talking about without checking the resources in front of you all the time, you're sadly mistaken.
Are you gonna edit that out?
No, it's the truth. I'm telling you the truth. Where are we? Okay, so I sort of told you how to do that.
Excuse me, Professor.
So let's talk about normal vectors. What? Again?
I think that U and V inverted in terms of the Z value. The bottom line, like U 1, 0, 1.5. If you plug it in, the first one is 3/4.
At the bottom.
Hold on.
5 minus.
So this was right.
Yeah,
Yeah.
I'm talking about the very bottom, like the values you plug in.
You,
Oh, yes.
right on the bottom.
Okay.
So
So
if you plug in 1 for u, then that's 5 minus 2, that's 3/4. And then, v is 0. So shouldn't that be 1 comma 0 comma 3/4?
here you're talking about?
Yeah.
1 comma 0.
And then you plug those two in to solve for
How do you do
No, that's fine.
Professor?
That's fine. What do I have in the first one? I have 1u plus 0v plus 0 constants. So it's 0 plus 1 plus 0.
Wait, how do you get those points? Like I did not get it.
And if I look at the v coordinate, I have 0 constants, 1v, and over here I have 3/4 v.
How do you get those points? Like,
How'd you get 1/2?
that, so 0.
Minus 2 divided by minus 4 is a half.
Oh, okay.
So 0, 0, negative 5, 4, you will let like x equal to 0, y equal
Think
to
of each coordinate in terms of the u's, the v, and the constant. So the second coordinate, how can you write it? There are 0 u's, there's 1 v, there's 0 constants,
Okay. So that would be
right? And then over here, there's minus 5 over 4 constants, there's a half u, and then there's 3/4 v. And so now, to get the constant point, I just pick all the constants, 0, 0, minus 5 over 4. To get all the u points, it's 1, 0, a half.
1, 0,
And to get all the v points, it's 0 v's here, 1 v here, and 3/4 v here. I'm separating in terms of constants the u's and the v's.
So to get, so you get the constant and then plus u. In the u, you will let.
This
u
is the
equal
vector
to-
that gives me the coefficients of the u's.
Okay, so.
And this is the vector that gives me the coefficients of the v's.
Okay.
And this is the vector that gives me the constant term in each.
Could you do
And so
one
this is
more
going to be a
example?
point in the plane. These will be 2 vectors in the plane.
Can you do one more example?
No.
When on the exam, do you rather us to give you the things on the top or the answers on the bottom? Like,
I don't care.
Oh, okay.
There are multiple ways to parametrize anything, so as long as your parametrization is correct, I'll know. There are literally an infinite number of ways to parametrize any given surface, so I don't particularly care. Just be correct, that's all I care about. How about normal vectors? I can probably do surface area at the same time. Because there's just a slight tweak in how you go from one to the other. Can I get rid of this?
Yeah.
So let me kind of explain the idea. So one thing I don't necessarily expect you guys to be self-sufficient with is proof. So usually if I'm proving something, I'm not going to be super strict on it. I just want you to get the idea of kind of what's going on. So let's say we have some surface here hovering, blah, blah, blah. And I kind of want to figure out, you know, a normal vector to the surface is where if you're at a point, you pick a tangent plane, the normal vector to that tangent plane is the guy rolled, right? So the idea is how we get that is we kind of slice this surface up, just like to do Riemann sums. So we slice up this surface into a bunch of approximately rectangular pieces, right? And of course, the more slices you make, the more these pieces will look like a rectangle. That's the Riemann sum approach where you're just going to do it an infinite number of times. But if you pick one of these pieces, just say I pick this guy, right? And let's just focus on that guy. Right, so we have this piece here. Right? Can pick one corner, and we can figure out 2 vectors in this piece. Let's say I wanted to figure out the vector here, and the vector that moves in that direction approximately. This is my R of u. So let's say this is my vector that goes in the u direction. How would I find that vector? How would I find the slope in the u direction?
dr with respect to u.
Find the partial of r with respect to u. That's going to give me the vector in the u direction. Similarly, find the partial of r with respect to v. That will give me the direction in the v direction. Okay? Now from this you can get two things. One, you can figure out what a normal vector must look like. Right? What would the normal vector at that point look like? The cross product, right? So we know that if we have two vectors lying in a plane, then the normal vector that you can create is just cross product the two of these guys. So this gives you the answer to one of the bonus problems in the last quiz. It's just going to be given by RU cross RV. Right? At the moment, we don't care about what direction it's pointing in because there are two possibilities here, right? One can be the negative or the other. When we get to orientation in terms of vectors, we'll worry about that. But for now, you can just know that a normal vector will have this one. I'm going to expand on that. Another thing we can do is to realize what would the area of this rectangle be? Well, it's not quite rectangle, it's an approximate rectangle. It's the absolute value of RU cross RV. That's again something you learned in Calc 3. So the area of this is going to be approximately RU cross RV magnitude. And how you can remember that is because you know that RU cross RV is just the magnitude of RU, magnitude of RV, sine theta, and then you can bring that back to the area formula that has sine theta in it.
Wait, I didn't get that. Was that part that you just said, that applies to this, or that was just like a proof?
Well, it's not really a proof, but this is a fact that we know from Calc 3. If I want to find an orthogonal vector to two other vectors, I take a cross product.
That part I get. I'm talking about the part where you were saying the area of the rectangle.
Okay, so let me... There's a formula that says, if you want to find the area of a triangle, right? Not necessarily a right triangle, but any kind of triangle. Let's say this side is A, that side is B. Then the area is given by AB sine theta. Right? So that's the magnitude of A, magnitude of B sine theta.
Wait, what formula is that?
Yeah, that's what I never saw that before in my life.
High school geometry.
So area of a triangle is 1/2 base times height, right? Why
That's
do-
one formula for the
How
area.
do you get the sine theta? Like, I have never seen this formula.
I can't go back to high school. This is a formula. It exists. Look it up. It exists. This is a formula. You can find a triangle. You can find the area of a triangle by this. Noticing that a rectangle is really just two triangles stuck together. You can just realize that the area of a rectangle is just going to be 2 times 1/2 AB sine theta. Right? And if you take the area, you just want to make sure you're taking a magnitude, and so you really get the magnitude of AB sine theta. But that's another formula for the cross product of the vectors A and B. So you get the area is this.
Okay.
Right? And so now, if you wanted to find the total area of the surface, what you're going to do is you're just going to sum over all these little areas. And so that's where the double integral comes in. Right? So that's the basic idea. I'm not really being specific here, but that's the general idea. So you pick one rectangle of the surface that was sliced into it. From that you can figure out that the normal vector has to be the cross product of those two vectors. And from that you can also figure out that the area must be, the area of that is going to be this. You add up all the areas of the rectangles, that amounts to, you're adding up along the u's and the v's, so you have two summation signs, which gives you two double integrals in the Riemann sum when you go off to infinity.
Is that cross product or you have the...
It's cross product, yes.
Yeah.
Everything here is a cross product. This is a cross product, that's a cross product. So it turns out the area can be given by the double integral of the cross product, the magnitude of the cross product. In other words, that's where you get the formula. That is the magnitude of the normal, i.e., the area of the surface is just the magnitude of the normal vector. Right? Now, how do you get to that formula that you learned in Calc 3? The idea is the following. Given, say your z is equal to a function of x and y. Parametrize in this way. Let x and y be themselves, and then just let the z be the f of xy. Right? And so now, if I use this formula to find the normal vector, so now I would know that the normal vector would be r sub x cross r sub y. It's going to be I, j, k. Partial f with respect to x, right? So, well, partial of this with respect to x is going to be 1, 0, and partial of f with respect to x. And with respect to y, it's going to be 0, 1, f with respect to y. If you take that cross product, what would you get? Plug everything this or in this column. This minus that, you get minus the partial with respect to x. In the middle, you get this minus that, you get minus the partial with respect to y. On the last side, you would just get 1. And so this would mean if you take the magnitude of the normal vector, you just get the square root of this guy squared plus that guy squared plus 1.
Wait, isn't that quite positive?
Huh?
Isn't the y, fy derivative is positive?
No. You remember you changed the sign in the middle, right? And so that's where they gave you the formula in Calc 3 that the area is just the integral of that guy. So this would mean that the area is the double integral of the magnitude of the normal, which ends up being the double integral of that guy. And that's where that formula came from. We now know 2 ways to find a normal vector. I kind of wanted to have this discussion later, but I guess now is a bit of time as any. So I will stress for you right now, being able to find normal vectors will be super important moving forward. So you need to be able to find a normal vector relatively quickly. It will kind of be the idea of, if I give you a ds integral, remember you have to find the arc length, right? But that's just a number that you're going to put inside the integral. There's a bigger context there, but you'll need to know the normal vector in order to find the integrals that I'll be telling you about. So being able to find a normal vector very quickly is going to be very important.
What was the second way, Professor? You said we know another way. What was the other way to find the normal? Aside from the first product.
Well, the idea is if I know that a surface is
No, I said aside from the cross product. What was the other way?
That there is no.
You said now we know another way. You just said now you know another way to find the cross product. So that's what I was saying. What was the
As in the form. That's what I'm going to describe now. Another way is to not do the cross product and just use this formula. Because you know the result of it. It's always going to look like this.
Oh.
So there are some instances where you don't have to do a cross product. You just know that's the formula.
Oh.
And there are some times where you can't use this formula, so you have to go through the cross product. And I'm going to tell you when you have to do which method. So let's talk about finding normals. Again, it's very important. Super duper important. Very, very super important. Okay. So now there are two cases. And each case you would do one way. Okay? So case 1. Case 1 is the surface is parametrized. By, say, R of UV. Then, that means you can take the normal vector to be RU cross RV. Right, so you'll go through, you'll do a cross product, and that will give you a normal. So that's one way. Case 2. Case 2 is, you might be given the surface as parametrized, but there's a special thing that happens. Case 2 happens when you can actually solve for one variable in terms of the other two. The surface is given in scalar form. Or you can figure it out in scalar form easily. I'm going to show you all the 3 variations, but it's just me switching around the variables. So for example, if your surface is given by, you can solve for z as a function of x and y, then you can always use your normal vector to just be that formula. Get a partial with respect to x, partial with respect to y, and y. The sign of these two must be different from the sign of the one. Okay? And these guys can be switched around. So if you can solve for the x as a function of y and z, then you would take your normal vector to be, now the x takes the role of the z in the previous one. So you'll put a 1 here, minus part with respect to y, minus part with respect to z. If you could solve for the y as a function of x and z, then your normal vector, the y gets to be the 1, and you take the partials of the other two. Case 2 is, of course, easier. Use it when you can.
What's the questions on the exam in this case? Case 2?
You'll have both versions. So case 2 happens when you can solve for one variable in terms of the other two. And if you can do that, then you don't have to do a cross product. That's what the answer is going to look like. So you'll just know the normal vector right away. Being able to find a normal vector quickly is important. If you cannot do this, then you're stuck kind of using the definition. You're going to have to take partials and then take the cross product of the partials. So let me give you some examples of that. Kind of do them off the top of my head because I didn't plan on actually talking about this at this point. But. So these are the two scenarios. If you can solve for one variable in terms of the other two, right, where of course these guys are the region of your projection, right? So this would mean that if you're setting up an integral, your dA would be in terms of dx, dy. This would mean if you're setting up an integral, your dA would be in terms of dy, dz, and this would be dx, dz, or dz, dx. Okay? So let me show you an example. Find a normal vector to say you're given that. How do you find a normal vector?
Put z in terms of the others.
Okay, and what would that look like?
Square root of 1 plus x squared plus y squared. Yeah. Yeah, minus x.
Not exactly.
No?
Do you parametrize?
If I tried to apply case 2, what would it look like? If I solve for z here, what would happen?
You get a plus or minus.
You get a plus or minus. And that can introduce all sorts of complications. It means you're splitting up the sphere into two parts. One is the top part and the bottom part. Which means normally if I give you an integral where you have to integrate over this surface, you'll end up having to do two sets of integrals because of that plus or minus. Okay? So you could do this, but you have to do two normals. You have to do a normal for the top part and a normal for the bottom part, which they'll give you opposite signs. So more than likely, this will double your work. If you're careful, you can kind of know how one might and just make minor tweaks, but more than likely you'll have to do two sets of integrals. In this case, what you'd probably want to do is parametrize. Because you can't really solve for z as a nice function of x and y. Your z really is two functions of x and y. It depends on which part of the surface you're on. Right? So probably better to parametrize. It'll be more difficult to find the normal vector, but to actually solve the problem at large, in general, it will be shorter. So it's kind of a give and take. Okay? So how would you parametrize this guy?
Spherical.
Use spherical coordinates. You know that the radius is 1, so you can do something like sine phi cosine theta, sine phi sine theta cosine phi. And then what you would do now is your n is going to be r sub phi cross r sub theta. I'll warn you, it will be annoying. But at the end of the day, you'll make up the time at the end of the problem. As opposed to now that makes all the difference in the world. The fact that they told you that, yeah.
For the y, wouldn't it be sine phi sine theta?
Yes, that should be a theta. Right? So given a full sphere, to sort of solve for one variable, you'll get kind of two functions that you have to work with. You have to work with one half at a time. So you're probably better off parametrizing. It's going to be annoying, I'm going to tell you. You can actually work this out yourself. But in the case that you're told this and you know that, then that's a big difference. Because now you don't have a plus or minus in the way, right? And literally if they told you something like x greater than 0, that's also easy. Or y greater than 0, that's also easy. You can solve for whatever variable they tell you is greater than 0, or less than 0. But let's say this is z greater than or equal to 0. So this means I can actually solve for my z. I know it's going to be the positive radical. There won't be two answers. And so I can immediately find my normal vector. It's going to be the partial with respect to x, the negative partial with respect to x, comma the negative partial with respect to y, and 1. Right? Now you can try this at home and you'll realize that you can't, it will be very difficult to just jump to that idea. Right? So you can have two different scenarios based on how you're describing your surface, which means you need to read carefully and look at the surface. Okay? Which is another thing that people got messed up with on the test 1. So in problem 5, I think, there was a part where I gave you a surface that was intersecting a plane. So really there was only one curve, but people didn't read properly, obviously, and so they thought they had to do like 4 curves. Right? So you have to be very careful with how you're reading. Right? So just mentioning something like this is very different from not mentioning something like that. Let me give you another example.
Professor, what is
Yes.
the test average?
I don't remember. I don't think it was good.
Does that mean you curving it since you like us?
No. Well, it's kind of typical for this class because usually students underestimate when I say how much Calc 3 you need to remember. And after the first test, then they wake up and like, oh yeah, and then they start studying their Calc 3 and then it gets better in the end. Okay, so what if you want to find a normal vector to this one? What would it look like?
Just the K vector?
It
Or
is
is that just like a
circle, it would be circle, so you can parametrize it.
That's a cylinder, right?
It's a cylinder.
It goes in Z forever.
In Calc 3, that's the equation of a cylinder, not a circle.
Oh,
It has 2
oh,
variables.
okay.
It cannot be a circle. A circle is one dimensional.
So z would be equal to 0 in this case.
No, Z can be anything. This is a cylinder,
It just expands only.
right? Which keeps going on forever. I want to find a normal vector, which means I need to find what? Just the guy that's pointing out here,
What? Oh, okay.
right?
So then for z instead of 1, we just put 0?
Not exactly. So what would you, so you might think, okay, let's just kind of use this shortcut formula, right? That would be the formula. We know that because we can parametrize that way and we'll get this equation. But what's the problem with that formula? Why you can't use that?
The same problem with this one, with the other one, plus and minus.
Well, it's kind of even worse than that. Where's the z? How are you going to solve for z as a function of x and y? There is no z. Another thing you can notice is that if this guy is pointing out directly perpendicular to that surface, what is its z component?
Anything.
Infinity.
Would it not be perpendicular to the normal vector?
What would the z component be? Right, it would be something, comma,
0.
0. That automatically means that this formula cannot work. So while case 2 is something that we want to use all the time, there are cases in which it's just not going to work. We can't force it to work. I can't actually solve for z as a function of x and y here, and I know for a fact that my normal vector should have coordinates 0 in the z component, but the shortcut formula has a 1. These are irreconcilable. So it turns out you can't use case 2 here. You'll have to parametrize. So here you must parametrize. Right, so then how do you parametrize that? How do you parametrize a cylinder?
R of theta and Z.
Theta and z.
Yeah, Z equals Z and X equals cosine theta and Y cosine theta.
So cosine theta, sine theta, it's a circle radius 1, and then your z will be itself. And then you can find your r sub theta minus sine theta, cosine theta, 0. And you find your r sub z, 0 comma 0 comma 1. And so your normal is just going to be the cross product of these guys. So that's your I, J, K. So that'll be cosine sine 0. Right? So now that makes sense with what your intuition is telling you. It has to be a 0 there. You couldn't use a shortcut formula because it forces you to put a 1 in the z component. So you come to an exam, you see this problem, and then you need to find a normal vector. You would know not even to attempt using this formula because it just doesn't make sense. I can't solve for the z, and I would need my z component 0. Doesn't match the formula, so you just immediately jump into parametrize, which by that time you should be able to parametrize a cylinder like that, and so you can get to this normal vector. What about this one? So I want a formula for a normal vector at any point to that surface.
This one will be the case 2.
We can use case 2 here. Here, we can see that y is given to us as a function of x and z. This means I can say my normal is going to be minus x, 1, minus z. And so that would be my normal vector, would be minus 2x, comma 1, minus 2z. And that would be a formula that gives me the normal vector at any point. What kind of surface is this?
Cylinder.
It's not a cylinder.
It says no.
It can be a cylinder. It has 3 variables in it. Cylinder happens when you only have 2 variables present, even though it's a 3-dimensional.
It's like it's like a bowl.
Hmm?
It's like a bowl.
It's a paraboloid running along the y, right, going this way. So that tells you you point a normal vector here, it'll be pointing in that direction. It's a paraboloid turned on its side. We'll talk a lot more about this because there is a fair amount of intuition that has to happen here, so we'll talk a bit about this next time. But finding normal vectors will be super, super important. We're going to use that all the time.
Professor, I got a question.
Yeah. Is it about this or something?
It is about that. That's a question.
From the
that I was
homework?
asking earlier from homework there.
Okay, all right.